This is the brief on covariant derivatives and physical invariance. So let's talk about the covariant derivative. It's this really crucial mathematical tool that makes sure physical laws don't just break when you start looking at them through a weird, distorted lens, like a stretched or bent coordinate system. Okay, so why is this thing so important? Well, it really boils down to three key points. First off, physical laws have to be consistent. It's a principle called physical invariance. What you measure shouldn't change just because your grid is curved instead of straight, right? The problem is, the standard derivative that we all learn in calculus, it totally fails this test. It kind of assumes everything is happening on a nice, flat grid. In curved space, that simple math just isn't enough. It completely misses how the grid itself is warping. Second, you might not even notice this as a problem in simple situations. But once you get into something like general relativity, where space-time itself is curved, using that standard derivative gives you answers that are just plain wrong. And that's because it doesn't account for how the grid is twisting and stretching as you move around. Finally, how do we fix this? That's where the covariant derivative comes in. It's a smarter derivative that adds a special correction term, the Christoffel symbol. You can almost think of it as a curvature fee. It's the exact piece that was missing, and it cancels out the error from the changing grid. This guarantees that your calculation gives you the true physical reality, no matter what grid you're using. So really, understanding the covariant derivative is understanding how physics makes sure we're all seeing the same reality on any coordinate grid you can imagine.